We have already seen the well-ordering theorem. It states that any set can be well ordered with some order relation. So it's a simple statement and we are assuming it to be true, although it can be proved from the axiom of choice. Now today we are going to use it to get to the notion of a minimal uncountable well-ordered set. And in that direction we have this simple corollary first. And the corollary states that there exists an uncountable well-ordered set. You may see that the corollary is a little vague in the sense that it doesn't really tell us what the set is. If you want the situation to be more concrete, you can consider the set of real numbers. We already know from real analysis that it's an uncountable set. So by the well-ordering theorem, there exists an order relation that will make this set a well-ordered set. So that way we can get an uncountable well-ordered set. Actually what the set is really not that important here. Its mere existence is what we need. Now before we get to that idea of minimal uncountable well-ordered set, we are going to need this definition. So this is the definition of a section of a well-ordered set. Say you have a well-ordered set X and you choose an element, any element alpha in X. Then for this element alpha, you define this subset S alpha of X to be the set of those elements X in X that are less than alpha. And this subset will be called the section of X by alpha. Now the next lemma is going to involve these things and will tell us something about that thing that we want to get, minimal uncountable well-ordered set. So this is lemma 10.2. What it's saying is that there exists a well-ordered set A which has a largest element which the author is calling omega, capital omega. You can call it anything actually, such that the section of this well-ordered set by that element omega, just like this S alpha, here we have S omega, is uncountable. That section as a set is uncountable, but any other section of the set A is countable. That means instead of choosing this largest element, if you choose any other element from A and you form, say that element is alpha, and you consider the section S alpha of A, that S alpha will be countable. So this well-ordered set has the peculiar property that precisely one section is uncountable but all other sections are countable. Now let's see how the author proves this. So the proof starts like this. It starts by considering an uncountable well-ordered set which by that corollary exists. Okay, any such set can be chosen. Again I am saying, if you find this just some letters a little bit too abstract, you can consider the set of real numbers here. However, do not forget that the order you are going to choose will not be your usual order. It's coming from the well-ordering theorem, which makes B well-ordered, or in your case R well-ordered. But anyway, we have an uncountable well-ordered set. Alright. Now we consider the Cartesian product of B and this two element set which has the integers 1 and 2. And this is itself an ordered set in the dictionary order. However, what are the individual orders on B and this? On B, of course, there is already an order which makes B well ordered. The simple order that you have in this case on this two element set is just that order which makes 1 less than 2, the usual order. Alright. Now, under the usual order, this is well ordered, right? Because it's a finite set and B is already well ordered. So, in the dictionary order, C itself will be well ordered. We have already seen that if you take the product of two, product means Cartesian product of two well ordered sets, then in the dictionary order, the Cartesian product becomes well ordered. Alright. Now, next we look at this fact about C. At least one section of C is uncountable. Why does the author say this? In fact, the author gives a hint. Let us see the hint in a bit more detail than is available in the text. Say you choose any element B from this B, and you consider the element 2 times B means you understand what this means. It's not the product of 2 and B, but it's the ordered pair with 2 as the first coordinate and B as the second coordinate. So, let us consider the section S by that element. Section in what? Section in the well ordered set C. Do not forget that sections have been defined only in well ordered sets. So, C is well ordered, so we are considering this section in C. Okay, fine. Now, the next thing to note is that this subset of C 1 times B means it is the set of those elements in C which have their first coordinates constantly 1. The second coordinate, however, are all the elements of B. You take all the elements and you get all these ordered pairs. These elements all belong to this section. Why though? Because by the definition of dictionary order, if you recall that image, of course you cannot draw any image here, but you can think of the elements of B as forming one column where the first coordinate is 1, and then next to that column there is another column. That's how the set C will look if you try to imagine it as a figure. And how does the order go in C? In the first column, which corresponds to 1, the order increases from the bottom element and it goes up. Okay. Up to what point we don't really know, that depends on B. And then you go to the second column and you get higher, larger elements, and there also it starts from bottom and goes up. So the order goes like this and then like this. And that's why all the elements, so this is the first column in that kind of imagination. All the elements in the first column are less than any element in the second column, and this is an element in the second column, 2 comma B or 2 times B in this notation. That is why this is a subset of this section, because the section by definition consists of all elements less than 2 comma B. However, if you note that it's not a very difficult thing to see that this ordered set has the same order type as B. But B is uncountable, so this is uncountable, and this is a subset of this section, so the section itself is uncountable. That means the well ordered set C has at least one uncountable section. Again, here also the existence of that itself just matters. Now, what can we do with this information? Let's see. Alright, so the set C, the well ordered set C, has at least one uncountable section. Let us next consider this set D. This is not how the proof occurs in the text. We are making it a little bit more detailed to make it more clear. So let's consider the set D next. The elements in D are those elements X of C which give us uncountable sections. That is, for them if we consider the sections, these are uncountable. Because C has at least one uncountable section, D is non-empty. We just need this non-emptiness. That is why we are not too bothered about what that uncountable section is. and D obviously by definition is a subset of C as well. Now you use the fact that C is well ordered. So you are now looking at a non-empty subset of C, and C is well ordered, so D must have a smallest element. Let's call that smallest element omega. Now omega, after all, being an element of D, immediately gives us what? It immediately tells us that S omega is uncountable because omega is an element of D. And next what we do, next we consider the set A, which is the union of S omega and the singleton set consisting of omega. So this will be that set A which is claimed in the statement. What is the claim? Let's recall the claim. The claim was that we want a well ordered set which has a largest element omega such that the section of the set by omega is uncountable, but all other sections are countable. Is that true? Are these things true for A? That's what we are going to see next. The author simply says that yes, they are true, but let us see in detail if they really are true. Okay, so the proof actually ended there itself. So we now want to understand if that really is the end. Let us see one by one these points. The first thing is that A is well ordered. Our set A, which is S omega union that singleton set omega, is well ordered. Why? Because A is a subset of C and C is well ordered. Any subset of a well ordered set is itself well ordered. We have already seen this. That's how A is well ordered. Next, let us take any element in A which is different from omega. Alright. So the definition of the set then forces A to be an element in S omega in that section, but then by the definition of S omega, A needs to be less than omega, and that makes omega the largest element of A. Okay, fine. Next we come to the question of S omega being uncountable, but that we already got there in the proof itself. And finally, we want to prove that the section of our set A by this element small a is countable. Suppose it is not true. Suppose that the section SA is also uncountable. But then what happens? If you go back to the definition of D, D is the set of those elements in C which give us uncountable sections. But see, A being an element of A is after all also an element of C because A is a subset of C. Now if on top of that it is giving us an uncountable section, then it qualifies to be an element of D. So that way A becomes an element of D. However, then omega is not the smallest element of D, which is how we chose omega as the smallest element of D. That is because A already is less than omega. So we get a contradiction, which means our supposition must be false. And that's how SA is countable. So yes, not only is the set A well ordered set and has omega as its largest element, but only the section of A by omega, that is S omega, is uncountable and all other sections are countable. So yes, the proof is correct. Next, let us see where we can go from here. Alright, so we have finally come to this stage where we have our minimal uncountable well ordered set, and that set is actually that S omega. But before we write that, you have that here, but let's note that S omega is itself uncountable. However, every section of it is countable, because every section of it means, you see, when we were considering sections of that original set capital A, there we had the largest element omega. If you instead consider S omega by removing that element omega from A, then here that omega itself is not available. So although S omega as a set is uncountable, but any section of this ordered set, it's a well ordered set, any section of this well ordered set by any element is going to be by some element coming from here. So automatically that element will be less than that omega. So that section will be countable. And in fact, it turns out that the order type of this S omega is determined by this condition, that the set is uncountable but every section is countable. Isn't this very strange? The set is uncountable, but the moment you cut it somewhere and chuck out that part, whatever you are left with, that is countable, that section is countable. And this is what we call a minimal uncountable well ordered set. So its existence has been established, that there exists at least one minimal uncountable well ordered set, and that is S omega. And in this context, we are going to denote the original set A itself by this new notation S omega bar. The reason for this notation will become clear when we learn closures of subsets in topological spaces. Okay, it will come when it comes. Now finally, there is a very useful property of this S omega that we see in the next result. So this is the result about S omega. The result says that if D is a countable subset of S omega, S omega itself is uncountable, but say you consider a countable subset D of S omega, there is a point where you may get confused. Note that all the sections of omega, S omega are countable. However, the sections of an ordered set, of a well ordered set, are not all its subsets. Okay, do not confuse that. Here D is just some subset which is a countable subset of S omega. Then D has an upper bound in S omega. Let's see how the proof goes. Okay, so this is how the proof goes. In the proof, what you do, you consider any element A of D. Oh, one more thing I must say at this point. You may have noticed, if you are following the book, you may have noticed that the author has used the letter A here instead of D. However, you may confuse this A with that previous A, which is S omega union singleton set omega. So I have decided to use the letter, some other letter, say D instead. But anyway, so for each element A in D, we consider the section SA. By the definition, or by, I should say, by the properties of S omega, the section of S omega by A, that is SA, is countable. So if you take all those SAs and take their union, let me call that set, say E, that must also be countable. Why? Any union of countable sets is not countable, but this is a countable union of countable sets. That is why it is countable by a result that you know very well. A countable union of countable sets is countable. Why is it a countable union? Because D is countable, that is why. There are a countable number of SAs. Alright. Now E of course is a subset of S omega, because each SA is a subset of S omega, but it's countable. S omega, however, itself is uncountable, so E cannot possibly be equal to S omega. It will be smaller than S omega, and that gives us a chance of choosing an element X in S omega which lies outside of E. Okay, it's in the complement of E. Now, what to do with this X? Suppose that at least one element of D exceeds X. Let that element be A. A exceeds X means we have this, that X is less than A. But then, by the definition of this section SA, X would have to be an element of SA because it is less than A. However, if x belongs to SA, then x belongs to the union as well, that is x belongs to E, which goes against the very choice of x. So this supposition cannot be true. So no element of D can exceed x. That means all the elements of D must be less than or equal to x. Do not forget that our ordered relation, the definition of ordered relation gives us comparability. It is because of that only we can conclude this when this is not true. In a partial ordered relation, which we haven't really discussed, you cannot say this, but we can say this here. But anyway, so we now have this. But what does this mean? This just directly tells us that x is an upper bound for D, and x is of course in S omega. So that's how we find an upper bound for D in S omega. This property is going to be very helpful to us later on whenever we discuss S omega. So with that, this section ends, and after this exercises will start. So that will be all for tonight. See you tomorrow with a new upload. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.